Welcome to MLOps Live, a podcast by Neptune AI.
We host in-depth discussions where machine learning practitioners answer questions from other practitioners about one subject related to production machine learning and MLOps.
Tune in to get real-life stories, dirty hacks, and pragmatic workarounds from ML people in the trenches. All right, we are ready to start another episode. So welcome to MLOps Live, everybody. I'm Sabine, your host, and I'm joined by my co-host, Steven. Our guests today are Jakub Zavrel and Fernando Rejon Barrera. The topic of today is data engineering and MLOps for neural search. So Jakub and Fernando work in Zeta Alpha, where they're building AI-based customized search and a knowledge navigation platform for research papers. Jakub is the founder and CEO, and Fernando is the senior infrastructure engineer. So guys, welcome to the show. Anything you like to add to the intro?
Fernando is actually our head of engineering.
Well, I kind of do a bit of everything.
Well, that's how it works in a startup. I also do everything.
All right, fair enough. Thanks for clarifying. So to warm you guys up, Jakub and Fernando, how would you explain MLOps for neural search in 1 minute?
Well, let's start with neural search. So neural search is very new generation of search technology, which completely breaks the boundaries of previous limitations of keyword search. So basically in neural search, you encode the query and the documents that you're going to search. You encode them as vectors using neural networks, hence the name, using very deep neural networks called transformers. And basically, once you've encoded your query and your documents in this vector space, you can do similarity search, kind of a nearest neighbor search, which gives you a much better recall of documents that don't necessarily have the word but have the same meaning. And you can also capture really complex relationships. So what is that challenge of MLOps there?
So in the point of view of MLOps, the biggest challenge is the fact that you have to reprocess all of your data every time you have a new model, for example, which goes a bit beyond the standard MLOps process for, let's say, models that are just serving live requests.
All right, thanks. I think that was pretty much 1 minute, so good job there. All right, Steven, over to you.
Awesome. Thanks, Kuba, for that. And I would love to know, for listeners who are unsure, what are some of the applications of neural search around us today, just to set the tone, right?
Yeah, so basically neural search is really good where a keyword search is not so good. So if you know exactly what you're looking for, keyword search is fine, right? Like you type your flight number or pizza in Amsterdam and you get pizza in Amsterdam. But for kind of unknown items or discovery, where you don't know which words are written in the document, but you still want to find it based on the meaning, that's really where neural search shines. And in fact, our application that we're working on at Zeta Alpha is to help researchers and engineers in AI and data science discover relevant new work, because there's so many new papers coming out all the time. But you don't necessarily know what are the latest trends in your area, which words they exactly use. So that's really where recommendations and discovery searches shine. But other areas where, like if you do multimodal search, for example, in an e-commerce setting, you have a shop and you're trying to find a piece of clothing by describing it, but the images are, just photos. That's really something you cannot do with keyword search, but you can do with neural search. And another area which is really strong is multilingual, right? If you query is in Dutch and your results are in Chinese, that's very hard to do using keyword search. So that's where neural search really changes the game.
Awesome. Thank you for for clarifying that. Now, here we are talking about the MLOps part of neural search, because you have the traditional research-based application of that, but also this is very valuable for things like search engine, like you mentioned, things that have to do with keywords. Now, I would love to ask, what are the main components of a neural search MLOps system? Because I think that was something that Fernando talked about, just setting up that MLOps system for this sort of thing, because I assume that there are problems and things like that. Well, we're going to get into that, but what are those main components you see when you want to put this into production?
So I can maybe walk you through a bit of the components. So let's say one part is the processing pipeline. So we collect documents from different sources, and then we have to put them in the correct way for them to be indexed. But also we need to select different parts of the document to create an embedding. So an embedding is a vector, and this is kind of the key ingredient in the neural search. Once we have the embedding and the data in the correct format, we index it, and the engine that is able to index it has to also work with vectors as well. In our case, we use both vectors and also traditional keyword search. And to be able to encode the vectors, you need a machine learning model, transformer-based model. So that's kind of the backend part. On the retrieval side, you also need to serve. So when the query comes, the query from the user, we encode it using the machine learning model, the same one that we use for
it has to be exactly the same one.
It has to be the exact same. And then once we have the vector, then we use the search engine to compare and find the best matches from the query.
Right, and this is it's becoming increasingly popular, right? Either people are building things themselves, or maybe they are using some managed service to do that, especially for their search engines. Now, some of those, like I know definitely when you're thinking about something like this, you talked about something about the embedding, which is like the data part, the processing pipeline. So what are those bottlenecks that I would sort of encounter when I'm trying to put these things together? Because I believe the processing pipeline, that's a huge problem itself because of the size of the embedding you have to deal with, and then managing the actual transformer models and so forth in production. So what are those bottlenecks I should kind of be aware of when setting this up?
Yeah, so I would say that the reprocess, so let's say you have a new model that you want to try out. As I mentioned at the beginning, the difficult part is that you have to go over the entire corpus and reprocess everything with that new model. And then you have to stand up an entire new set of services and infrastructure to support that new version, so that you can compare it with the old one, for example. So let's say the bottleneck would be to be able to have enough resources in your backend to do the computation quickly enough. But also at the same time, the more documents you collect in your index, the index will grow. And then you have to manage how the index can scale and perform, will have the same performance as before.
Yeah, and to add to that, I think it's really important for everybody in the audience to realize that these large transformer models, they don't run on CPU, right? They run on GPU.
Right.
Otherwise, the whole thing becomes way too slow. So essentially, a lot of the complexities are around scaling out the provisioning of GPU machines, and especially if you run on Amazon, like we do, spot instances are like way cheaper than reserved instances. So when you scale out, you're trying to get hold of spot instances, which is not always very easy.
Right. Maybe something that I can mention regarding that is that the workflow that you use for the processing is completely different from the one that you use for the real-time inference. And so you would benefit from having a lot of GPUs accessible during reprocessing. And so, as Jakub mentioned, it can be very hard to get the spot capacity available.
Perfect. And I would love us to zoom into your use case a little, because your use case has to do with deal with text embeddings and so forth. Which embeddings do you use for your text engine, and how do you decide on choosing these embeddings? The one you use for your text, your paper, searching for papers and so forth. What sort of embeddings do you use there?
Yeah, so we went through a whole journey since we started with this about 3 years ago.
Right.
The sort of naive, these are all transformer models, right? So like kind of based on BERT style language models. And the sort of naive thought is that you can just take embeddings directly from BERT and then use a sentence encoder or something like that, and just put these embeddings in your search engine. And when you do that on a kind of a little toy data set, and then you type one query, it kind of works, but it doesn't give like substantial good search performance, like in terms of relevance over a traditional BM25 search. So we went through a whole journey, kind of both at the same time adapting to our domain of scientific documents, but also at a certain moment realizing that models which are fully unsupervised, they don't work really well. So almost everybody in neural search is relying on models that were trained on MS Marco, which is a very large question document data set with relevance judgments. And then you can add your own flavors on top of that. For example, query to document is a very similar but slightly different use case from finding similar documents to a document. So there are more like citation informed embeddings in that space, which are better for document to document, whereas MS Marco ones are better for based ones are better for query to document. But usually you also have like the problem of domain adaptation. If you take something which is just pre-trained on MS Marco, you apply to scientific documents or e-commerce products or in a different language, it won't really work well. So you always need to kind of look at domain adaptation as well.
Right. And I assume there's going to be that trade-off between the quality of vectors that, you're using as well as the size. And how do you manage that sort of trade-off between like the scale, that's a huge amount of embeddings you have to deal with, as well as the quality of embeddings you're actually using for the project?
Do you mean like the size of the embeddings or the number of them that you have?
Yeah, pretty much the number of them, and which ones are actually relevant for type of problem you're solving.
So I think it's these transformer models are pretty large vectors. Like 768 is a pretty like sort of default dimensionality for BERT style models. You can go a little bit lower than that by using kind of smaller or distilled models, but you lose a little bit of performance. And how do you measure that sort of resource quality trade-off? Really by doing information retrieval experiments, by doing end-to-end search, and then benchmarking the relevance. So basically scoring the documents searches and optimizing for information retrieval metrics like NDCG or MRR. You cannot do it in a more simple way, probably.
And again, we have quite a number of questions on retrieval, because I presume that's like one of the hard problems. So we have those ones from like the community. We're going to be sharing that later on. I think we have the question from the audience.
Yes, we have a question in chat from Zishan. What was the training strategy and how did you enforce similarity between similar documents?
Yeah, so I can go a little bit more into that. So there are many approaches which are kind of unsupervised, right? So you have some sort of, or self-supervised is maybe the better way to say. For example, in the scientific domain, you can take documents that cite each other, so that there's like a reference between them in the citation part. You can take these as positive examples, and documents that don't cite each other as negative examples. You can also do kind of you could say, completely self-supervised. If you crop a document in a certain way, and you crop it in another way, you get a pair of documents which kind of originated from the same document, but they're slightly different. And you can basically these transformer models are like bi-encoder architecture. So they take one and the other representation, and they try to move the positive examples closer together and the negative further away from each other. And you can generate these positive and negative examples in many ways. We learned kind of the hard way that unless you also use specific query document examples, like supervised data from queries and documents, you're not going to squeeze out the optimal performance.
And just to follow up on Zishan's question, how do you set up the evaluation for something like this? I mean, I'm thinking about the end-to-end pipelines and worried about embedding, retrieval. How's the evaluation setup like?
If you talk about retrieval quality, right?
Mm-hmm.
Right, not like engineering evaluation, like end-to-end testing of the pipeline and stuff. Maybe Fernando can go into that a little bit later. But if you're talking about like search evaluation, there are standard benchmarks, right? Like all kinds of track collections, MS Marco itself. There's a new pretty good test collection called BEIR, BEIR, which consists of many different benchmarks, like a collection of many different benchmarks. I would definitely recommend looking at that. But if you're looking at a particular domain that you're working in, like e-commerce product search or scientific document retrieval or medical documents or legal documents, you really want to build at least a small curated test collection yourself that really reflects the judgments of experts in your domain. And that doesn't have to be super large, right? You don't need to manually label like millions of documents. For our domain, we work with a collection of about 100 queries. And that means you have a couple of thousand relevance judgments, and that gives you kind of the temperature of the water and tells you whether you're moving in the right direction when you're training.
So how about the end-to-end pipeline?
What we do in general is we do like test every step of the pipeline to make sure that it just follows the standard software development techniques. But in terms of, for example, something to take into account, for example, when we're importing more data or new sources, is that the results may vary. So then we have some, I guess, kind of automated way of evaluating that, right? So we have had before, like we dump a huge collection from a new source, and maybe the quality of the embeddings was not so good because of the source, how the source was created, and then you can see that it affects the search results. So when you search for something, you might find these not relevant results on top. And then this is something that we can check for before actually releasing either choosing not to release it or to fix it, to fix the pipeline.
Yeah, but what I think is important for everybody to understand that if you want to evaluate like a new type of model, you basically need to re-index everything, and at the same time make sure that the vectors in your index and the real-time encoding of the query that you use to send to the index is all upgraded to the new version. So basically, you need to deploy like a development version of the index and then test on that.
Oh, awesome. I think we have a question from the community.
Yeah, thanks, Zishan, for the question, and thanks for your thorough answer. So Gerard has a question. Did you explore possible ways to retrieve parts of documents, for example, to focus on literature review or conclusions?
It's a great question. We had the same discussion today over lunch, actually. So right. Obviously, there's kind of an old saying in neural information retrieval: how much information can you cram into a single vector, right? If you take like a 250-page book, or like somebody's PhD thesis, it's very hard to encode it in one 700-dimensional vector, right? It's impossible. So typically these transformer models have a fixed length of input that they can process, usually around 500 tokens, so a little bit less than 500 words. And once you go beyond that and you want to search like in the depth of the document, you really need to go to passage retrieval. So that means that basically you split up your whole document into smaller passages, and then each and single one of them goes to the vector encoder with the transformers. And that multiplies things by a lot.
Yeah, so from point of view of the engineering, you have to really consider like what is the benefit of the quality of the retrieval, because as Jakub mentioned, if you go from encoding the whole document to encoding the passages, it's like a factor of 30, and you can even go further and say, okay, each passage might be composed of different sentences, and
you could do it per sentence, right? And to the question, like, you absolutely need to do this kind of passage retrieval to be able to do that. Does it help to kind of restrict the documents or the passages to particular sections of the document, like the experiments or the data sets, or, in theory, yes. But the discussion we had over lunch today is like, okay, so how many queries from our query logs actually need that kind of sophistication? And I think for like 95% of your queries, you can do with simple passage retrieval without actually parsing the whole document out into sections.
Cool, thanks very much. And we actually had a second question or follow-up question from Zishan. So when a new query comes, do you compare with the entire database of embeddings, or is there a strategy to look into a selective portion of data?
So the engine, well, I guess the typical way in which engines are composed is that they use some approximate nearest neighbor algorithm, so that you can quickly compare from the entire data set what is the closest vector, but not going one by one, comparing them. Is more like approximating. And the trade-off there is that you need to keep this index or this graph in memory, in RAM. So the more vectors you have, the more RAM you need in your nodes.
Yeah, so it's a kind of index structure. If you want to read more about that, the state-of-the-art algorithm is called the HNSW, hierarchical navigable small world maps. And that's kind of a indexing algorithm where you don't have to go through all the index sequentially, but you kind of quickly zoom on the region which is most similar. The downside of that is that it's not guaranteed to find the most similar document. It finds it in like 95% of the cases, which on average is good enough to work with.
Awesome. We have a question that was pre-submitted from the community. And this person is asking, my team is doing a lot of things, a lot of work with embeddings, and in particular, embedding similarity searches. Can you give us an insight into the considerations we should make when selecting embedding similarity search tools and maybe databases? Should we even consider one? And can you make recommendations from your own experience?
So one thing that you have to consider is, of course, the corpus size. So as I mentioned before, if you're using this approximate nearest neighbor algorithm, you need a lot of RAM, or like as much RAM as vectors that, or like documents that you have. So from that point of view, you need to consider like, how not only how are you going to split the text to create the vectors, but also like how many resources you are going to need. And so that's kind of one consideration in terms of tooling. Maybe Jakub, you can go more into the model part, like how do you create embeddings and what those tools are?
Yeah, so I think there's a lot of packages that implement this kind of approximate nearest neighbor search, either as Python libraries, like the classic is Annoy from Spotify. Then Facebook came with Fice, which is used in a lot of tools. Nowadays, there's like specialized vector search engines from a bunch of startups. There's also integrated solutions or more mature solutions in things like Elasticsearch or Solr, or things like Vespa, for example, is a good kind of hybrid search engine, which provides both neural search and classical search. So it really depends on what you exactly need in terms of scaling and specific problems that you're trying to solve. There's even managed solutions. Well, we are actually one of them, Zeta Alpha, but you can also use OpenAI or Google to manage, or even Amazon, I think, to manage this kind of nearest neighbor search for you. Each has their pros and cons, but I would definitely check them out. There's some pretty good blogs on the different vector search engines out there.
Awesome. So can you make any recommendation?
It really depends. So there's if you're looking for like a fully hosted solution, or you want to deploy something yourself, that's fully open source and you can tweak everything. There's a bunch of sort of infrastructure startups which make these vector databases. Some examples of them are Quadrant and Weaviate and Milvus. Pinecone is, I think, a fully managed one. We actually chose to go with a solution which is integrated in Elasticsearch. It's called OpenSearch, and we like that because it offers all the sort of performance benefits of these vector search engines, but it also offers all of the sort of engineering infrastructure for scaling it out horizontally, managing it, serving it, and scaling it out across infrastructure.
Yeah, I will add to that also, for example, depending on the requirements, you might want to not only have vector search, but also do filtering. And then, the out-of-the-box solution for that would be something based on Elasticsearch or some of the others that you mentioned. And also, whether you need to, maybe we can get into that later, but there is some things with post or pre-filtering. So whether you're going to reduce the set of vectors that you want to look for by saying, the color of the t-shirt has to be black. And then, that has other considerations when you want to select a search engine.
Yeah, and t-shirts always have to be black. I don't know any other color t-shirts.
Right. And there's a good follow-up question, I think. And this person is asking, in terms of choosing an embedding similarity search tool, do you think a self-hosted library, just like you've mentioned, the open source solutions, would be better than choosing a SaaS platform, especially at the early stage when we are not dealing with large number of embeddings or large couples or things like that?
I would consider that a non-technical question, right, because it really depends on how many people do you have to manage it? How much development time are you going to spend to build? Because the vector search engine itself is not your application, right? It's just like a database, essentially. So yeah, are you better off with self-hosting your SQL database or going for a fully managed solution? Depends on who you are and what you're exactly looking for. I would definitely prefer myself to have something that's open source at the heart, so that you can kind of, that you can tweak it in all kinds of ways if it doesn't fit your needs. But if you don't have resources for that, then managed solution makes more sense.
Yeah, definitely.
Okay, perfect. Thanks for that. And we have another question from the community, and this person is asking, do you have any experience with neural search applications, like deploying neural search applications inside a Kubernetes cluster? If you do, what was your experience and how did you go about choosing your technique and the tools you probably used?
Yeah, we do actually run everything, all of our services and platforms in Kubernetes. And I guess the question there might be some related to operators, whether you have access to Kubernetes operators that provide you some sort of management of the, let's say, the engine. And in our case, we are not using operators, and that is kind of one of the pain points of using our solution, and because you need to do kind of manually, say, for example, when you want to replicate a cluster, or then you have to do it manually. But also, for example, if you're running out of space, what does that mean? That you need to do some certain some operations on the cluster to replicate the index, and then make sure that both of the replicas are in sync and so on. So that could be covered by operators. For OpenSearch, there is an operator for OpenSearch, but as far as I know, it doesn't have this kind of high-level management. In terms of deploying models, there are also multiple solutions. So you can go from, as we do, just write your own wrapper around the model, just a simple API wrapper that gives you your prediction endpoint. Or you can have, things where you just drop the S3 model, and then it automatically scales for your requests and so on. But it will depend, of course, on your requirements, on the traffic and the requests that you are receiving.
Yeah, but from my sort of more non-sysop experience, I would definitely recommend going for Kubernetes, because in my previous company, we were running everything kind of native on just with Docker images, and that's a bit of a nightmare to manage. And we actually had a team of 10 people managing just the infrastructure, and here it's not even a full-time job. I don't know.
Yeah. Kubernetes is a way to go for me as well.
All right. Thanks. We have a question in chat again from Richard, this time about evaluation. So what are the best ways to go about evaluating a retrieval system, and what are the considerations for choosing an evaluation?
If you're looking at search quality, traditionally that's defined as relevance, and you have a bunch of metrics that kind of look like at the ranking, right? So essentially, neural search always will retrieve documents, right? It's like the closest vector in the vector space is the top, is the number one result, and then the second could be completely somewhere else in the vector space, but it's still the number two. So, but it doesn't matter, right? For information retrieval evaluation, you just want to look whether that document satisfies the information need posed by the searcher with their query. So you can just score documents. We typically do score them with like a 0, 1, 2, a non-relevant, highly relevant, somewhat relevant scale. And we typically score like the top 10 results, like the first page, basically, for a whole bunch of different queries. So we make a collection of kind of very representative queries that are similar to what our users would be asking. And then we mark all of these top 10 documents with 0, 1, and 2. And then you can calculate metrics like, for example, NDCG, precision at 10, recall is somewhat harder because then you would have to mark a lot more of them. But MRR is also very useful because typically you want your top 1 result to be better than your top 5 result. So MRR is the measure which most effectively measures whether your highly ranked documents are more relevant than the somewhat lower ranks.
Awesome. Thank you. Thanks, Richard, for the question.
Perfect. And we have another question from the MLOps community. And this person is asking, we are starting to use nearest neighbors over embeddings for similarity search quite heavily. Do you think running the similarity search within the training set is more likely to return instances of the same class than if we run it with inputs not in the training set?
I'm not sure what is meant by same class here.
Okay.
But let's assume that you mean like just finding instances with the same label, right? So obviously, if the document set that you train on, you're going to move as I said earlier, the kind of positive examples of documents, you're going to move them closer together. So let's assume that the class label determines what are positive examples, and you're going to move on the training set the instances with the same class closer together. Yeah, then absolutely you will have a little bit of overfitting on the training set with these large networks, and you're more likely to do well in classification on your training set than on an independent test set. So sometimes that's all you have, and then that's like, in if you write academic papers, it's called cheating, looking at your test set or testing on your training set. If you're talking about applications and that's all the data that you have, then that's what you have to work with. So for your users, it might still give better performance than doing the proper academic research setup.
Awesome. And I'm thinking, let's move away from the evaluation part of things now. Start thinking about testing. So how do you test this, your sort of embedding pipelines? Do you unit test, or what are the traditional tests you do, or they're very, very specific ones?
Yeah, so we do a unit test for all of the stages of the pipeline. Also some integration tests. I mean, we do have maybe some dependencies. For example, if you are going to call the model, that you have to assume that the response has the correct shape and so on. But yeah, those are kind of basics, software engineering type of test, because the other tests, like if you want to know how the model is performing, then it has to be more like, as Jakub mentioned before, like look at the statistics. For example, we record the actions of the user, for example, the interaction of the user with the search results, and then we store those so we can later evaluate, how the performance of the search engine, like that.
Fernando and I come from two different worlds. I'm kind of a weekly typed, scruffy guy from the Unix world of the 1990s. So for me, like strongly defining the schemas and like all the ontologies and attributes is somewhat of a but I guess Fernando has a different position, and he's our head of engineering. So we have a lot more specification than I would normally do.
Yeah, I mean, there are pros and cons, of course, but I think like catching these kind of trivial mistakes before you are in production and things live is way more cheaper to do it that way, to catch it in the compiler or like in the IDE before you go live. Of course, the con is that then you have a bit more overhead, and the cost of change of the types is a bit harder and so on. But I guess it works out.
Move a little bit slower, and break a little bit less.
Yes.
Awesome. So I'm thinking, let's dig deeper into like the text search. I'm just kind of curious if maybe if that's part of my application, and I'm starting to think about, worried about text embeddings and generally just deploying such systems, such engine to production that would have to do with text embeddings, not image in this case, of course. What should I be aware of when I'm, getting started, just thinking about these things, and what are the common issues I may sort of encounter when building such engine? I think it's more of a proof of concept. Listen, we're going to talk about scaling up later, but let's talk about proof of concept now.
I think like a lot of the things is like when you have a new model. So if you have one model and that's all, it's not very complex. You just have to grab your search engine, you have to grab your embeddings model, and then you serve it. The complication comes when you try to actually deploy a new model, because as I mentioned before, you have to reprocess everything, and also like you have to keep track of multiple versions of the data, right? So like if you have new model that creates new embeddings, you need to track like, okay, this is version 2, and you cannot delete the old one or overwrite it, because if you want to roll back, then it has to be there. And as well as standing up all the infrastructure, like a new index and so on, to have that serve the new embeddings, as well as the model, right? So I guess you have to be very agile in creating this infrastructure. Right? For me, that means like being on top of Kubernetes. That makes it very easy to do that. Still, there are challenges, of course.
The challenges are really on the relevance and on the high quality of the search results. because like with neural search, a neural's like a vector space search in an embedding space, it will always give some results, right? There's always some point closest to the query, but the models, because of this kind of cosine similarity in high dimensional space, the models don't really know when they're like out of their domain and very low confidence. So that's one challenge that you will have to deal with, that sometimes your top results are kind of very irrelevant, and you need to figure out why. Another really kind of engineering challenge with these neural search things is when you combine traditional sort of filters and these approximate nearest neighbor searches. That approximate neighbor search works in such a way that if it gives a much smaller result set because of this index structure, but it may be that none of the vectors in that smaller index structure actually satisfies your filters. So if you do the filtering after the nearest neighbor, you might end up with 0 results, where a full nearest neighbor search with filters would have actually given you results. So there are all kinds of tricks to deal with that. That's a very specific technical challenge for neural search deployment.
Yeah, we have a question from the community, but I'll just throw a follow-up question. And then, when this sort of proof of concept now is scaling, what components do you think will fail first as it scales? Your number of embeddings you're storing are growing and things like that. What are the components you've seen in real time that fail first when this sort of scaling occurs?
So I guess it depends on what solutions you chose at the beginning, right, in the proof of concept stuff. But I will say, like, if you did it like we are doing, like, for example, with Elastic-based in this search engine, managing adding more and more documents to the index is not so easy to scale, because you need to actually create a completely new index with more shards. That's how the data is distributed across multiple nodes. So if you have more vectors, like, they don't fit in your machine, because as we discussed at the beginning, it has to do a lot with the RAM, and you cannot typically scale the RAM vertically. You can do it up to some point, but when you need a new node and then you need more shards, you have to actually create a new index and maintain both replicas in sync while you are doing that process. So yeah, I think that's kind of, it doesn't, it's not something that just crashes, but actually it can crash. If you run out of RAM, for example, it can crash. So I would say that's pretty critical to have, good capacity management before you start scaling.
I think the thing that will fail the most quickly is your compute budget, because it's just a way more resource intensive, both on RAM, on GPU, and on compute in general, and on storage as well, because you have all these very high dimensional double float vectors on disk, and especially the GPU part can kind of grow pretty quickly in terms of cost. So horizontal scaling is easy technically, but paying for the bills is a more complex thing.
So it's the cost that will fail. Awesome, thanks.
All right, so at this point we can take yet another follow-up question from chat. So Zishan would like to know, how do you decide on a similarity threshold when considering how similar two documents are?
That's very hard, to be honest. So basically, you have to benchmark it, right? You're gonna throw a bunch of queries that are representative, is the evaluation part I referred to earlier, and then you're gonna map out the sort of the similarity distances, and there's always kind of a precision recall trade-off, right? Like if you're doing something like patent search, you want to make sure that you don't miss a relevant patent or in legal, right? Recall is really important. So then you're gonna set a really low threshold. If like us, you're gonna, for example, be sending research papers, like recommendations to researchers via email every day, if they are relevant, you want to set the threshold pretty high, because they don't want to get flooded with just a bunch of kind of related papers. So it's really very domain specific, and you have to tune it using evaluation benchmark sets.
Awesome. So I'm kind of curious, what do you think I should spend the most time, whenever I'm setting up like an embedding similarity search, for my use case, whether it's vision or text, where do you think I should spend the large amount of time for my use case itself, considering like whether it's a stack, I'm considering you've talked about a stack earlier, but just generally just modeling my problem.
I hate to emphasize evaluation, but it's really, there's no silver bullet in neural search. You're really using it to get better relevance for particular use cases, right? That's the whole goal of the exercise. So looking at your data that you're used for evaluation and actually doing that evaluation, that's where I would spend most of the time. You can get pretty far with, let's say, off-the-shelf embeddings models. You can get very far with standardized vector search tools, or even very common infrastructure like Solr or Elasticsearch these days. So don't spend your time looking at shiny objects, but really making sure that it works for the user.
All right. Fair enough.
It's also, I think it's a very difficult problem. Like, I mean, as a scientist, I would say first understand the problem real well before you try to come up with a solution. And, trying to determine what is the best or most relevant results is not so black and white, right? So I guess, as Jakub said, like really understanding what is the thing that you want to improve, or what the user experience is going to be is very important.
Yeah, and just to make a little plug there, I think like 2 years ago, neural search did not work, not better than classical BM25 information retrieval. It's moved so rapidly that now it's beating BM25 on most of the common benchmarks by a pretty significant margin, especially if you have supervised in-domain training data. Like MS Marco is more than 2 or 3 times as good as classical search. And the field is moving super fast. So like every week, there's a new research paper coming out, which again improves the state of the art on neural search. And one, if you want to stay up to date, try Zeta Alpha, because we're actually delivering these research papers on a highly relevant basis. And second, follow the benchmarks and kind of try to keep up with this very fast development.
Awesome. We have one more question from the community, and this person is asking, realistically, do you need to update, retrain, or fine-tune text embeddings as new data comes in? Or can you just keep the embedding model static and just index new data? Probably in your case, I think that's something you're probably doing with your research papers, or, how do you go about it?
I think the algorithmic side, kind of the improvements in the basic methods and encoders are more fundamental than adapting to the domain drift of your documents. So typically, also because it's so expensive to to re-index everything with a new embedding, you don't want to do that too often. You want to prove the point that it's substantially better than what you had before. And just new documents coming in is typically not a reason to retrain anything. So you can see the embeddings model as more or less static, until you have a new candidate out of your data science research group, or something new is published on Hugging Face or whatever. So you're not retraining as you're using the search system.
Yeah, and it might be that also is some. For example, in our case, we grab documents with kind of heterogeneous data. It might be that it's just in the processing, right? Maybe you are grabbing the wrong part of the document to embed it, and it's not really the embedding model that is wrong, but just the way the document is coming in from the source.
Yeah, but sometimes you will need to deal with it using retraining. So, for example, we had scientific papers. We added GitHub READMEs to our search engine, documents that are kind of very different in their language and their content and their length. And we did run into serious problems with the existing model, so we had to change.
Awesome. So I'm curious, what are your war stories building this stuff? What war stories do you have for us?
I think the war stories are mainly about failures that we want to sweep under the carpet and never talk about again.
Right.
But I think one that I would like to mention is our sort of really naive first approach, where we're just taking CLS tokens out of BERT and embedding those, shouting victory, like, hey, it works. We have a vector search engines, we have embeddings, we have semantic search. So that's a pretty bad one. I think one thing that we're really kind of a good war story is we built this new feature, which is like a PDF reader. So researchers can read papers and then like annotate parts of the document. So you can like make a little, take a little segment of text and put your little comments or notes to it. And then we just build this amazing new feature, which is contextual search. So you can just take this note and launch a related work search. And we didn't have to do anything other than throw the query into the neural search. And that was a pretty like victory moment in terms of war stories.
Awesome.
Yeah, I believe we have a question from the audience. Arturo, would you like to go ahead?
Yeah, hello. I have a question concerning the evaluation states. You talk about collecting a high quality data set for the evaluation. What is the process for this? Is it completely manual? And what is the considerations that you had to take?
It's completely manual, unfortunately. But you can reuse it, right? It's like a benchmark set, so it evolves over time. So if you start with a small set, like 50 to 100 queries, and you score the top 10 for all of those queries with your current system, you will see that you now have a benchmark. Then you change your embeddings, for example, and you get you get new documents in the top 10. But some of the documents in the top 10 will remain the same. So that part you can reuse, but every new document that pops up, you're going to need to make a new manual judgment on that. So unfortunately, it's largely manual, but as your models get better and better, the amount of manual work decreases.
All right. I think we're getting to the end of this session, and it would be a crime not to ask this particular question. And I would love to know, how early are we in this field of neuroscience? Because, you mentioned something like over the past 2 years, there's been tremendous growth, right? And, how early are we in the field of neuroscience and deploying such applications? And what do you think the future looks like? What would you like to see?
Well, I remember like when I started, of course, I wasn't so familiar with the industry or like the search and neural search part. But I feel like more and more I'm looking, for example, if I'm looking at Hacker News, like there is always like push towards different search engines. And I think neural search is kind of one of the ways where you can improve the quality, for example.
Yeah, so it's really about quality. And I think by now, neural search is more or less the standard in terms of quality. Is not the standard in terms of engineering yet, I think, because it introduces this somewhat extra complexity. But we're seeing with our customers that that basically a lot of queries require neural search to be successful. As usually, kind of the big tech companies are setting the standard. Actually, neural search is already under the hood in both Google and Bing, right? So it's kind of the mid-sized companies and smaller products that have to follow to kind of set that example. I think the ultimate goal is to have a search engine which simply understands you, right? And always gives the right search results. And my bet would 100% be that search engine is going to be working on the principles of neural search and not on the principles of the previous generation of keyword-based search.
Right. In the final minutes, what would you like to see going forward?
My dream is completely serverless GPU inference.
Yes.
Okay.
Let's have that.
Awesome.
And for real cheap.
Yes.
Awesome.
All right, excellent. So before we wrap things up, could you guys tell us how people can follow what you're doing and connect with you online?
Yeah. So for those who are interested in neural search specifically, we have a podcast series where our Sergi Castella and Andrew Yates, who's a professor at the University of Amsterdam, discuss in these chairs with these microphones here the latest papers on neural search. It's on YouTube, so check that out. We also do a monthly webinar and go to a lot of conferences and report from these conferences. So check out our blog on zeraalpha.com. And we're pretty active on Twitter, tweeting about the latest papers in this area and many other areas of AI. So if you want to check that out, Zera Vector is our handle there.
Awesome. Thanks so much for sharing your expertise and broad experience. It was great to have you. Thanks also to all our participants and questions. So we'll be back in 2 weeks, as always, on the 22nd of June. And next time, our guest will be Michal Tadeuszak, and the topic will be managing computer vision projects. So, as always, you can submit your questions in advance as well. If you cannot make it, you can join the MLOps community Slack and submit your questions or talk to us about anything MLOps related. And as a final reminder, the podcast is launched, so you can catch up with previous episodes on Apple Podcasts or Spotify or wherever you listen to your podcasts. So thanks again, everyone. See you soon and take care.
Thanks for having us.
Bye-bye.
Thanks very much. Bye-bye. MLOps Live is brought to you by Neptune AI. Remember that you can join us live at the next event and ask your questions. We run it every other Wednesday, and you can register at neptune.ai/events.
And then make sure to search for MLOps Live in Apple Podcasts, Spotify, Google Podcasts, and anywhere you get your podcast. Click follow and don't miss any episodes.
Thanks, and see you next time.